Thanks for the great introduction. But you stole my introductory question. I always ask people two questions at the beginning of this talk. First one is, who knows Zalando? So everybody has raised their hand. But the second and more important question is, who has actually bought something at Zalando? Let's see a show of hands here. Oh, actually, the German crowd is pretty good. You guys have bought a lot of stuff at Zalando. And I love to see that there's lots of men who have bought stuff at Zalando, too. A lot of times, it's just like, just the ladies raise their hand. I'm like, men, you know, Zalando is the great place for guys because you're not being harassed by some sales lady the entire time. And you can just shop, look good in the private of your own home. So I'm a big fan of Zalando. It's the right tool for the job if you want to look great. But that's not what I'm going to talk about today. Today I'm going to talk about reinforcement learning and why that's the right tool for the job. And so I actually used to work in construction before I got into mathematics and data science. Fun fact. I learned very quickly that there's the right tool for the job and there's the wrong tool for the job. It's totally possible to take a pair of pliers and hammer in a nail with it. You know, if you're too lazy to get down off the ladder, you can do that. But it's not recommendable. And so, but to visualize like what's the right tool for the job, what's the wrong tool for the job, I've collected a bunch of pictures of the wrong tool for the job. I think if we can visualize the wrong tool, then we'll know what the right tool is. So let's get started. Trash can as a ladder extension. It's really like, trash cans are great for collecting trash, but putting it underneath your ladder, I mean, I don't have to say why this is a bad idea. A coat hanger as, like, I don't even know what they're trying to achieve here exactly, but you know, having your coat hanger so close to the electrical outlet, it's totally not the right tool for the job. In Germany, they call this their 1 Euro Grill, the €1 barbecue. It's I give points for creativity. And then this one, okay, let's see it on a show of hands. Who's done this? Okay, yeah. So half the people have done it and half the people are lying. Everybody's done this. Everybody stood on the office chair to get something, and we all know that the office chair is not the thing you're supposed to stand on. It'll roll, you'll break your neck. It should be in all these compliance trainings. Like, the number one thing, don't do at work, is standing on the office chair. But yes, it's the wrong tool for the job, but everybody uses it. So then one last thing is for my friends and family in Texas. When you're going to pick up your kids from school, please take a car where you can actually see if a child is in front of the car. If you can't see a child in front of it, the car is too big and you shouldn't be using it to pick up your kids from school. That's enough said on that one. So what's this got to do with Zalando? What's this got to do with reinforcement learning? Well, I'm going to talk about what's the job we're trying to do at Zalando, and what's the job we're trying to do in enterprise AI in general. Then I'm going to talk about what's the wrong tool, what's the tool we've been using a lot already. And then I'm going to talk about reinforcement learning, which is, surprisingly enough, the right tool. So let's get started. What's the job? What's the job at Zalando? What's the job in enterprise AI? So at Zalando, we want to show offers which excite customers. We want to encourage fuller engagement with the platform. So that means that if there's lots of different products on the platform, right? So we have the shop, but we also have things like used clothing, Circle. We have the lounge, which is very much promotion-based. We want to encourage customers who have engaged with one product on the platform to engage on others. We want to set prices to maximize profit, and we want to recommend sizes which your customer will keep. Right? And so I'm sure that at your company the problems are different, but you can sort of see how there's similarities here. And so to do a bit of a deep dive into one of the problems that we try and solve, it's the encourage engagement. So one idea that was come up with to help encourage engagement was to do this get to look tool. So the get to look tool, you can go to this URL, and and it shows you images of influencers. So influencers, you can also become an influencer yourself if you want to and upload some pictures. And these images of influencers are shown to you, and they're supposed to inspire you. So I went there just as a little experiment to see how I'm going to be inspired. And I got these pictures on the top. And I'm sorry, it's just like a white dude in white pants with white shoes and different white jackets. So I mean, the jackets are actually different. The shirts are different too. But I mean, honestly, like, let's see a show of hands. Who's inspired? Okay, nobody's inspired. Me neither. And so I think I didn't make this tool, but I think that what's going on is behind the scenes is that there's a prediction that's happening. There's some sort of predictive model that predicts what I'll click or what I'll like, and then it sort of shows the maximum likelihood prediction. And this makes it to where you're going to get very homogeneous results at the top. And so clearly this like inspiration isn't working so well. And if we think about it, if we think about the problem of inspiration, well, inspiration is not actually a prediction problem. You're not trying to just like predict what's like the most inspiring thing, because there's probably lots of different things that could be inspiring. You want to show these like different, possibly inspiring things. And you're sort of creating an interaction, right? Where the customer, you show something, maybe the customer clicks, maybe the customer doesn't click, and then you learn about the customer and you build up this interaction with the customer. And so, since it is this interaction, it becomes actually a control problem, and you can model it with this same sort of picture or this same sort of model that one uses for reinforcement learning and for robotic control and all sorts of other stuff, where you have an agent, and the agent then is the recommendation, the search, the platform in general. You have a state, and the agent then takes the state, makes an action, the environment sort of returns a reward and a new state, and then you try and get your agent to maximize the reward. In the recommender example, it would be like this, right? So you have your agent, that's the platform, as I said. The state would be the customer's history, everything that the customer has clicked and done up until now. The action would be the recommendation you show or the inspiration you show. The environment is your customer, and then the customer decides to click, maybe purchase, maybe wish list, and the customer's history gets updated. And you iterate like this. So we see that the problem we're trying to solve isn't really a prediction problem, but it's a control problem. So what are the tools that we've been using so far? What's this sort of wrong tool that we've been using at Zalando? And I think that a lot of people in enterprise AI have been using. Well, let's get back to these problems we're trying to solve. The problem I've been dwelling on, show offers which excite customers. The tool that's used is we predict what recommendations a customer will click, right? So we've turned this control problem into a recommendation problem, and we see, you know, I showed you where this can go wrong, but it happens with other things too, where we try and encourage fuller engagement. There's always some sort of personalization effort, but this is very difficult since you're trying to get somebody to engage with something they've never engaged with, and you try and use personalization on that. So that's always going to be a bit tricky. Set prices to maximize revenue, right? There you forecast demand for the rest of the season, but this is tricky because the prices that you set influence the demand that you have, and then the demand you have influences the price that you set, and so on and so forth. And so just using a prediction is going to cause you problems there. And then recommend sizes which the customer will keep. Here, predicting sizes generally does work fairly well, but there's also a little bit of interplay because sometimes people think that they have one size, but actually they have another, and if they finally sort of break out of that mold and get the size that actually works for them, then they'll do a little bit better. And there you can also cast it as a bit of a control problem. To summarize, what we see that what's often done is to use supervised learning to train a model and do what whatever action the model predicts will get you the highest reward. And I call this prediction as a policy, right? So you're making a prediction, and then your policy is whatever this prediction says you should do. And so why is prediction as a policy the wrong tool? Well, if the predictions are generally correct, then it works great. Let's just be honest with this. But a lot of times predictions aren't correct. And since the predictions aren't correct, it oftentimes takes a bad action. And since you have a lack of exploration, right, you have a bunch of different actions you can take. Since you're always taking the bad action, you're not exploring new and better, potentially better actions, you don't discover that the actions are bad. So let me walk through an example here that really illustrates this. And let me just be clear, I got some questions about this, about the nitty-gritty details of how this is rolled out. This is not an actual thing at Zalando. This is not an actual product. This is just an example product using generated data. This is not real customer data. We do not have customers that are 0 or 1 years old. It's just an example to help illustrate everything. But let's say that we have a heuristic policy that shows customers campaigns based on their age, right? So we show younger customers between 0 and 40, we show them the blue campaign, and then older customers between 40 and 100, we show the red campaign. And then we see sort of the profit that we get from the campaign being shown. And we can already sort of see from this that we're probably not showing the best policy. It seems like in the 30 to 40-year-old range, we probably could do a little bit better by showing the red campaign. And so like a good data scientist, we say, okay, well, let's model this. Let's do predictions of policy. We fit a model to the two different campaigns, and we discover from our little regression model that indeed the blue campaign is not really the right thing to show to our 20 to 40-year-olds, and the red campaign would be a better fit. And so we then update, okay, and we start showing the red campaign to the 20 to 40-year-olds, and we get a 2.6% uplift in profit, and this is quite nice. And we say, okay, we're good data scientists. Let's not quit there. Let's keep on going, and we can sort of retrain daily, right? And we see that our prediction errors decrease nicely as we go down. And our profit sort of goes up over time as we retrain daily and collect more training data. And we get this 2.7% profit uplift. So it seems pretty good. It seems like we're doing the right thing. Training errors going down, profits going up. I mean, what more could you want? It's every data scientist's dream. And this goes really nicely until disaster strikes somehow. And a random... And for whatever reason, the policy sends out random emails, random campaigns. And when this random policy is used, for whatever reason, this is the data we get. And we see, all of a sudden, actually our fit was really bad in areas that we never explored. If we look at our older customers, 80 to 100-year-olds, they really respond well to campaign 2. So, to the blue campaign. And it's something we only discovered by accident. It's something we only discovered because we started sending out these random campaigns. And then if we fit again, we see, okay, we could have gotten a 14.2% uplift, So that 2.7 or 2.8% that we got beforehand, it seemed pretty good at the time, but now we realize it was fairly miserable. And so what went wrong? Well, the problem is that just fitting to past data, it can really lead to a suboptimal policy. And although this can probably be fixed with some sort of epsilon greedy exploration or some sort of temperature soft mass heuristic, it's actually a deeper problem. And the deeper problem is that inference methods, they're just made for inference. They're not made for control. But we see that in enterprise AI, we're trying to solve control problems. And there's just no guarantee that these inference methods will solve the control problem. And so it seems like inference methods it's the wrong tool for the job, and we should use something better. So I'd be remiss not to talk about what the right tool for the job is. I'd be remiss to leave you hanging and not tell you what it is. And of course, since I do research in reinforcement learning, I think reinforcement learning is the right tool, and we'll talk about that. So this problem is an example of what we call a contextual bandit problem. There's a hierarchy of problems in reinforcement learning. Contextual bandits are one of the easier ones, and a lot of problems that we solve in enterprise AI can be cast as contextual bandit problems. So before you go out and try and implement the latest and greatest from DeepMind or Google Brain or whatever, I would recommend sitting down and saying, well, is it a contextual bandit problem, and trying to come up with a policy that solves it as a contextual bandit problem, see how well that works. And only after if you've got the contextual bandit as a good baseline should you go on to more complicated things like Markov decision processes, all this deep Q learning, and all this other stuff that's much fancier, but much more difficult. And so the contextual bandit problem, what happens here is, given a context, so the context is the customer's age, we try to discover the optimal action while collecting as much reward as possible, right? Because we could obviously just do random policy for a year, and then after a year we've got a ton of training data that will make a very good prediction about what to do, but this would be very costly. So we want to balance sort of this cost of exploration, this cost of perhaps sending out the wrong campaign, with exploitation, with sending out stuff that we know works. Yeah, so exactly. As I said, it's a balance of exploration and exploitation. And for each context, we just have to figure out what's the right thing to do, what's the right action to take, send the red campaign, send the blue campaign. Contextual bandit, you can also have, you don't necessarily have to restrict yourself to just actions, a discrete number of actions. You can also have continuous actions. But we're going to just show the discrete number of actions because it's easier to visualize. So how can we solve it? Well, one way is to treat it as an even simpler problem, which is the multi-arm bandit problem. Who here has heard of multi-arm bandits? Okay, so I'd say it's about half the people, so I can quickly explain the multi-arm bandit. So the multi-arm bandit is contextual bandit without the context. You just imagine you're in Vegas, you have a bunch of different slot machines, and you want to know which one has the best payout, right? So some of them pay out 80%, some of them pay out 90%, some of them pay out 99%, right? And you want to find the slot machine that pays out the highest. And so you have to go around, put your coin in a slot machine, pull the arm, see what happens, and over time you get to know each slot machine and get to know which one's best. And if there's one where you've put in your coin 5 times, and each time you've gotten absolutely nothing, then you can be pretty sure that one's a bad slot machine and move on to other slot machines. So you're balancing this exploration and exploitation just with multiple slot machines. And you don't worry about the context. So here we're casting this contextual bandit problem as a multi-arm bandit problem by doing some binning. What we've done is we've taken our customers by decade and just split them up into 10 different bins. And then for each bin, we come up with a confidence bound for the profit of this bin. So if we look here at the 10 to 20-year-olds, right? We see that we have a lot of blue dots there. We have a lot of blue training data. So we can be fairly confident that the profit uplift for the 10 to 20-year-olds is going to be somewhere between 0.7 and 0.8. On the other hand, we only have one training data point for the red campaign for the 10 to 20-year-olds. And that means that we have a much wider confidence interval. Now, one way to solve a multi-arm bandit problem is to always take the action with the largest upper confidence bound. So this makes it to where we're encouraged to explore. If we're not very confident about what's going to be happening in a certain area, we explore there by always taking the thing with the largest upper confidence bound. In the case of our 10 to 20-year-olds, if another 10 to 20-year-old customer is going to come along, we're going to take the red campaign because it has the highest upper confidence bound. We're not very sure about what's going to happen there, so we do that. Upper confidence bound, it's a simple and it's a proven algorithm that balances both exploration and exploitation and quickly gets you to a good performance. If we run this for 100 steps, then this is what we end up with. And we see it's actually pretty good. So for our 80 to 100-year-olds, for example, here we know that the blue campaign is a lot better. And we see that in the next 100 steps, right? We've had 100 steps of the old campaign, of the old heuristic. That's the small red dots. And then for the next 100 steps, the big dots, where we're collecting more data, we see that we've really only done the blue campaign for the 80 to 100-year-olds. So we've both explored, learned what we've explored, learned how this works, but we've also exploited, and we've shown the campaign that works best. In the 10 to 20-year-olds, there's like really a mix of blue and red dots because there the two campaigns lie very close to one another. They're sort of equally good, and so it's always exploring both and trying to figure out which one's better. And so this is how we can do it with multi-arm bandit. But you can imagine that it's a bit problematic since we're actually learning 20 models at the same time. We're trying to learn 20 different things at the same time. We're trying to learn how the blue campaign works for 10 different groups of people and how the red campaign works for 10 different groups of people. And so it's a lot of parameters to learn, and it probably takes a good bit of exploration till it really converges and really works well. So how can we do it better? Well, the better way is to, instead of learning these 10 different parameters for each campaign, we can learn a parametric model, right? So this is just a linear regression model, and we're learning not the parameters of the linear regression model, but confidence bounds for the parameters of the linear regression model. So this linear regression model only has 3 parameters, and we see that if we just learn the confidence bounds for the parameters of the linear regression model on the data from our heuristic, it looks quite nice because where there's lots of data, the confidence bounds are very narrow, and where there's little data, the confidence bounds get larger, meaning that we'll end up exploring in areas where we haven't explored before. How does this work? Well, it's actually quite easy. You can just do linear regression, and with linear regression, you can always do this inverse matrix, and since the noise is Gaussian, you can also invert the noise and then sample from your parameters. And so this is, I think, like 50 different samples of the parameters, and then you just take these samples and take confidence bounds based on these samples and get that confidence interval. And so now, if we do just 10 steps, right? If we do 10 steps, we see 2 things. First, we see we're exploring in areas where we didn't explore before. Where there's lots of blue data beforehand, we have some red dots, meaning we've explored what happens if we do the red campaign where there was only blue data. And in areas where there was only red data, we see that we get lots of new blue dots because it's exploring there. And we also see that our confidence bounds shrink. We get more and more confident about what's going on. After 100 steps, we get this. We get our 14.9% uplift, which is quite good. Even better than just training on random training data. So then the big question is, well, if we're already solving RL problems, if in enterprise AI we're always trying to do control problems, why aren't we using reinforcement learning methods? Why is it that everybody still uses prediction and inference methods? And I've got a couple of observations. So I think that I've got 6 observations actually, but 4 are on the screen, and then I'll give 2 more. First two have to do with inference methods, which is that prediction accuracy gives you a false sense of security. You see that you're good at predicting, and you think, okay, since my predictions are good, the policy must be good. But it's not the case. You can actually build pathological examples where you have two predictions. One prediction is better than the other, but the prediction that's better gives you a worse policy. It's very strange, but it can happen. And this leads to observation 2. It's often not obvious when a policy isn't working well. Then there's two sort of observations that have to do with cognitive biases, which is you have this Maslow's hammer cognitive bias going on. So Maslow once said, if the only tool you have is a hammer, it's tempting to treat everything as if it were a nail. And I know that when I was learning data science at university, I learned a lot about supervised and unsupervised learning. And since those are sort of the tools that I was given, when I went into industry, those are the tools I used. And since those are the tools we know, you also have this illusion of explanatory depth cognitive bias, which means that you think that skills in one area will be good at solving problems in another. You think, okay, because I'm good at predicting, I'll be good at control, but it's actually two different things. I've got two more observations that I didn't put on the slide, but after watching the great talk on ML ops, I thought like these two observations fit in nicely too, which is to do this, you're not doing batch ML anymore, right? Because you really have to update your model really quickly. Because if you don't update your model really quickly, if you're stuck with this for a whole day, then you're going to be exploring a lot in areas where you should probably quit exploring after you've collected some data and after your confidence bounds have shrunk. So you really have to update a lot quicker to make this work. And a lot of people are sort of afraid to get away from batch ML and do this stuff in real time. And then the last observation is that A/B testing this is actually really difficult. The last observation is A/B testing is really difficult because if you have one thing that's exploring and the other thing that's just learning from the training data, then the thing that's just learning from the training data will work really well because the other thing is exploring for it. And it'll seem like one thing is working well because the other one's doing all the work of exploring, right? So you have to come up with a good way of doing A/B testing. But the summary here is you use RL methods for RL problems. So I want to end the talk with a fashion example. So you probably are thinking, okay, Kelvin, you made all these great claims about how the inspiration isn't inspiring. Now put your money where your mouth is. Show us some inspiration. Show us something that actually works. And I did that for you. So the question is, can we improve on uninspiring inspiration, right? So we've got a synthetic wish list history here on the right. Yeah, GDPR compliant is synthetic, but we have this synthetic customer who likes sort of different types of high heels, right? So we've got stiletto high heels, but we also have boots. We have high heels with wider platforms. And then if we train a prediction on this, the result just isn't inspiring. And it's not inspiring because all of these shoes are really stiletto heels. The colors are different, but we see there's no boots and there's no heels that are wider. It's all very similar. But if instead we use upper confidence bound, we get really inspiring recommendations. We see here that we get some boots, we get some slippers with a bit of heel. We also get different sort of sandal-shaped shoes, right? Sandal heels. And it's not all stuff that the customer has bought. It can get a little bit away, but these things can really serve as an inspiration for the customer. The same goes if we look at men's shoes, right? So we've got this guy, and he's like a bit of like a work and play type guy, right? So we've got some work shoes, this black shoe, some loafers, also some fun shoes like these sneakers. And if we get the maximum likelihood prediction, it's just all black shoes, right? If you find this like row of black shoes to be inspiring, then I'm sorry, I really can't help you. Okay, out of time, but this last slide. And if we use upper confidence bound, then we see it works really well. Because we have both the work shoes, we have the fun shoes, but we also have a bit of stuff in between, and a bit of stuff that the customer hasn't bought, but maybe the customer would find really interesting and really inspiring. And so I hope that now you're inspired to use the right tool for the job. I thank you, and I look forward to your questions.